Hello, I'm Kim Ross, President and founder of Rethink Energy Florida. We're pleased to be the Florida host of this webinar on one of the most salient energy issues in Florida right now. If you are joining this webinar, you probably know that the legislature has no fewer than 7 bills related to hydraulic fracturing, acidization, and other well stimulation forms for the production of oil and gas. Yet many people don't know what these processes entail, and even fewer know about the relevant scientific studies that have been conducted. Some of you who have seen me testify in committees will know that Rethink Energy Florida stands with dozens of other organizations supporting a ban on these practices in Florida. However, the scientists you are about to hear from do not take policy positions or make policy recommendations. At Rethink Energy, one of our values is to provide evidence-based information. That is why we're pleased to host the Collaborative Laboratories for Environmental Analysis and Remediation, or CLEAR, at the University of Texas, Arlington. Let's let the science speak for itself. On to introducing our speakers. Dr. Zachariah Hildenbrand is the founder of Inform Environment, LLC, and also sits on the Scientific Advisory Board of CLEAR. Dr. Hildenbrand has coordinated projects in the Barnett, Klein, and Eagle Ford regions of Texas, and this work has produced more than 20 peer-reviewed scientific journals and journal articles and textbook chapters. Dr. Hildenbrand is determined to provide a further understanding of unconventional drilling and to develop solutions for groundwater, soil, and air remediation. Dr. Kevin Shug is professor and Shimadzu Distinguished Professor of Analytical Chemistry in the Department of Chemistry and Biochemistry at the University of Texas at Arlington. His group specializes in the development and application of methods for separation and detection of chemical species in complex mixtures. He has been recognized for his research and teaching efforts based on awards from the American Chemical Society, Eli Lilly and Company, and the University of Texas System, among others. He and his group have published 100 peer-reviewed scientific articles, including extensive work in environmental analytical chemistry. Dr. Doug Carlton is the project manager of CLEAR. He is trained as an analytical chemist in chromatographic separations and tailored detection systems, predominantly applied to the environmental sciences. Throughout his doctoral program, he is a recipient of the UTA Department of Chemistry and Biochemistry Graduate Research Award and the Charles K. Baker Character Fellowship.
My name is Dr. Zach Hildenbrand. I'm with my colleagues Dr. Kevin Shug and Dr. Doug Carlton. And in addition to a number of other scientists from other universities, we collectively comprise CLEAR. CLEAR stands for the Collaborative Laboratories for Environmental Analysis and Remediation, and our facility is based out of the University of Texas at Arlington. It's a tremendous pleasure to have this opportunity to talk about unconventional drilling and the environmental implications for Florida. Basically, we can provide some insight and recommendations resulting from our experiments that we've collected data from all over the state of Texas. And so this is going to be an interactive platform for you folks to engage with us. We've got a live Q&A session. You can type in your questions as need be, and then we also have a handout which you can download, and we encourage you to do that and to print it off. It's in an accordion fold format, so it's actually in an actual brochure that we'll be able to take a look at and provide a lot of information about what CLEAR is all about and the research that we've done. So I'm going to go ahead and get started into how we got involved in this field of research. We're a multidisciplinary collective of scientists coming from different fields of research, different backgrounds, to report on this important issue. I myself, I'm a biochemist by training. I was previously working on cancer biology, particularly on blood-borne cancers. My colleague, Dr. Kevin Shug here, he is a world-class analytical chemist who has worked on a number of different fields of research. We also have one of his students who is also a very established analytical chemist, Dr. Doug Carlton. They can tell you a little bit more about their personal story. But how all of this got started was in 2011. We came together, just a couple of friends, and it was the result of some of the documentaries we were seeing out there, things like Gasland and Fracnation, where there seemed to be an over dramatization of here we go, we have a slide of it. It seemed to be an over-dramatization of the implications of hydraulic fracturing. And so you have, here we have images of fracnation, which is a very pro-industry take. You have Gasland, which appears to be somewhat of the antithesis of that. You also have actors getting involved, artists. You have the Incredible Hulk, Mr. Mark Ruffalo, and then you also have Mr. Good Will Hunting, Matt Damon, who produced Promised Land. So when you start to see these forms of media, you think like, well, they must be making an educated assessment of this hydraulic fracturing process, this unconventional drilling process, to be making these claims. And the truth of the matter is, in 2011, that simply was not the case. There was literally no peer-reviewed literature on this important topic. So we all kind of came together in this multidisciplinary band of friends and scientists to go out and collect samples in the Barnett Shale region of the Dallas-Fort Worth Metroplex and to report on the quality of the water in these regions, which has over 20,000 gas wells in the area. So the hypothesis was that if gas wells are having an effect on drinking water quality, it would be likely that as the water wells got positioned closer to these gas wells, that you would start to see more abnormalities in the water. And so that was really the start for us. So I'm going to get into a little bit of the background of what this whole unconventional drilling process is, and particularly as it pertains to the state of Florida. So there's really nothing new or unconventional about unconventional drilling. Unconventional drilling is merely talking about the different formations. And now we're starting to talk about these deep shale layers where they're extracting oil and natural gas. The different processes that they're using for this include hydraulic fracturing, which uses a large amount of water, sand, and chemicals to stimulate the shale layers. And we're talking about, on vertical wells, we're talking anywhere from 1 to 3 million gallons to horizontal wells where they're drilling vertically and then moving horizontally, upwards of 15 million gallons of water. So it's a tremendous amount of water that's being used. Also, there are a process called shale acidization, which they're using large amounts of hydrochloric and hydrofluoric acids to dissolve complete petrolithic zones to acquire the oil and natural gas. And based on the geology in Florida, with a lot of the limestone formations where they'll be stimulating, this appears to be where a majority of they'll be using the shale acidization as opposed to hydraulic fracturing. Anytime you are drilling these unconventional wells, you're going to have a tremendous amount of flowback or produced water, which is going to be laced with the chemicals used to stimulate the well, in addition to naturally occurring radioactive material. It's going to contain a lot of salt and brine solutions, and they need to dispose of that waste in some way. So in some cases, as we've seen it in West Texas, these waste solutions are put into pits where they're kept and they either evaporate over time, or they're pumped into these underground injection wells, also known as saltwater disposal wells, which penetrate into large brackish water formations tens of thousands of feet below the surface. There are a number of environmental concerns associated with unconventional drilling. We're going to touch on a number of them. These include concerns over groundwater and surface water quality, soil and air quality, and certainly as we get into dealing with these industrial fluids and carcinogenic compounds that are used during the stimulation process, there are the concerns over the human health implications. Also, we do know that accidents do occur. Here is an image from Kennedy, Texas, in the Eagle Ford Shale. This is South Texas, where they experienced a blowout where the pressure in the well resulted in a loss of well integrity, and you had a large spewing of chemicals and hydrocarbons into the atmosphere. As you can see, this picture was taken shortly thereafter the blowout, resulting in a large devastation of the land. Our team has been out in this region, gone out and characterized the water, soil, and air quality to understand the extent of the damage. Additional environmental concerns include increases in seismicity. Since the inception of unconventional drilling in Kansas, there's been a 12 100% increase in earthquakes in Kansas. There's also been increased seismicity due to wastewater injection, these saltwater disposal wells in the state of Oklahoma. And earthquakes in Azle, Texas, in the Barnett Shale have been linked to underground injection and these unconventional gas wells. There are also concerns over surface water contamination anytime you're dealing with these waste pits, fluid spills and pipeline leaks, and of course the major concern is groundwater contamination. A lot of times, or all the time, these wells are the aquifer is protected from the oil or gas well with protective casing. However, there is research showing that protective casing fails at a rate of 12% within the first year, and thus increases subsequent years after that. So obviously, if you're dealing with an area like the Barnett Shale region here in Dallas-Fort Worth, you have 20,000 gas wells, and if 12% failure rate, then potentially you have the opportunity for there to be a number of contamination events over time. Okay, I'm going to hand it over to my colleague here, Dr. Shug. He's going to talk a little bit more about the chemical composition of this.
Hi, everyone. It's really a pleasure to be able to join you today to talk about a bit about our research. Zach's done a great job of giving an introduction to hydraulic fracturing, unconventional drilling. Just a little bit more background on the composition of fracturing fluid. This is an area that people have looked at very closely in terms of the concept of hydraulic fracturing and its potential environmental impact. Zach mentioned an enormous amount of water can be used to stimulate these horizontal or vertical gas wells. Up to 3 to 5 million gallons per well is kind of an average, and then assuming you have some up to 2% of different additives that might act as biocides, surfactants, gelling agents, emulsifiers, corrosion inhibitors. And in general, these can also contain things like BTEX compounds, which is a short term for benzene, toluene, ethylbenzene, and xylenes. The thing is that, and this has always been a difficulty from the beginning, is the exact recipe for these mixtures is proprietary. And although there are some lists, such as at this fracfocus.org or a congressional report in 2011 that talk about bulk use of different compounds, we really don't know at any one given site what exactly is being used. And so we have to make sure that our analytical methods are tailored to be able to look for things that we think are used commonly, but also looking out for things that we might not know we should be looking for. Along with the water and chemicals, we have proppants. Those are used to hold the fractures open once after the stimulation event. And then in terms of shale acidization, we could be dealing with large quantities of hydrochloric and hydrofluoric acids, and these are really quite nasty, strong acids that can be difficult to handle. So specific concerns, I mean, unknown mixture of chemicals and no true transparency, that's difficult. No tracers are used. There are many aspects and many steps to the unconventional drilling process, and it becomes difficult then to trace where the actual event of failure happened, if it did happen. And one might think that incorporating tracers in through different parts of the processes would be a best practice that could be pursued. Once you get the mixtures of chemicals underground, it is going to mix with brines and the underlying liquids that are in the shale formation. And when all of that comes back up, it makes for a much more complex mixture to handle. And in the volume that this is being performed, fluid spills and accidents become a concern in terms of handling that waste and disposing of that waste properly. When we get to the disposal of wastewater, this is one area that has come to light, I think, much more recently as another true concern of the unconventional drilling process. And in the past, there's been a lot of work, a lot of talk about the unconventional drilling the hydraulic fracturing process specifically, but the disposal of wastewater, I think, is equally concerning. We've done quite a bit of analysis for, initially just to understand the complexity of the wastewater, but then as moving forward, we're trying to also work with different companies and with other professors here at the University of Texas at Arlington to develop means for treating this wastewater. And you can see here a short list of some compounds that we found in some samples of wastewater. This was published earlier this year in the journal Water, a peer-reviewed article. And things that you would see in here are not typically things that you want to have interfacing with your groundwater, need to be handled very carefully. Things like methylene chloride, toluene, and xylene are parts of that BTEX family. Bisphenol F is it's a plasticizer, a chemical additive that's known to have endocrine disrupting capabilities. So just having an ability to characterize these different mixtures is extremely important. We luckily have at our fingertips a large swath of instrumentation based on our partnership with Shimadzu Scientific Instruments. In this case, we were using gas chromatography, mass spectrometry. The shale acidization, I think, is an important topic, especially for those of you in Florida who are watching this. In general, when we talk about unconventional reservoirs, unconventional versus conventional, it's really talking about the porosity of the underlying rock layer from which they're trying to extract the natural gas and oil. What we need to use is unconventional techniques when you become a very non-porous or extremely tight formations, such that these formations have been trapping that oil and gas for a long, long time. You need to come in there and break that up with the hydraulic fracturing. Or if you move to a little bit more to the right here, towards the conventional side, Florida's geology is characterized by a significant amount of limestone. And it's in this types of formation where you're kind of going between the tight and low, higher porosity and lower porosity environments that you might switch between a hydraulic fracturing or larger use of shale acidization in order to liberate those oil and gas reservoirs. So if we want to characterize environmental quality, there really are some primary considerations that you'd like to have in place. We'd love to have baseline measurements in an area that's about to undergo unconventional drilling. But that was difficult for us here in Texas. We have been successful and currently have a study in peer review that we'll talk about a little bit later where we were able to sample before, during, and after drilling. But in the Barnett Shale, there's been a lot of activity here much before we were able ever to go out and collect samples. So the baseline measurements are ideal. All the peer-reviewed literature asks for it. But in such cases where we have a very developed area here in Texas, it can become difficult. For those of you in Florida, this is absolutely an opportunity to understand the water quality before going into unconventional drilling. After that case, you'd love to have a series of scheduled monitoring events where on a regular period of time, these water samples or air or soil samples can be collected and studied in a very systematic fashion to understand if there are going to be any major changes over time. And if there are changes, to be able to act on them and understand what the source of that problem is so that it can be fixed before a major problem can ensue. To do this, we need to have a whole series of different analytical tools. When we came into the game, a lot of there was very minimal amount of work, as Zach had talked about, and that work was really focused on methane detection. We've taken a more holistic approach and developed a series of analytical methods that can look at pretty much any chemical compound, metals, ions, minerals that are present in water. And we use these tools to really comprehensively assess the water quality. And then we're constantly looking at the development of new technology, whether that's going to be remote monitoring, different sensors, whether it's going to be mobile technology. Again, these are some things that Zach will get a chance to tell you a little bit about later on in the presentation. So when we get to a water well site, we have a handheld probe where we're going to collect a basic series of water analysis parameters. We would take the sample as close to the water well as possible. We don't want to get any influence from pipes in the houses or whatnot. And then that water is purged for up to about 20 to 30 minutes until the pH and temperature is stable. And then at that point, this handheld probe can record on-site the pH, total dissolved solids, salinity, conductance, temperature, and other parameters that we consider bulk properties of the water that we can then relate back to later on with our more detailed chemical analysis. So these measures on site allow us to quickly monitor change in water chemistry, and so this might be a point for a quick and easy testing that can be done regularly. And then when there's a problem, we'll take these samples into the lab, or if we are going to do a baseline assessment, we'll take these samples in the lab where we can characterize them more comprehensively. We have developed a whole series of methods. One of our mainstays is based on gas chromatography. We'll do a series where we have a mass spectrometer detector. We'll monitor for a whole series of compounds, such as the ones listed here. We have borrowed best practices from standardized EPA methods. We include rigorous validation, analysis of blanks, and quality control to ensure that the measurements that we're making are very reliable. And then we monitor not only for these chemical compounds, which we know to be commonly used or common constituents in hydraulic fracturing mixtures, but also build our methods so that we can be on the lookout for anything new. The technology is constantly changing, and to be able to keep our eye open for any new chemical signature that might show up in the water is extremely valuable and important. For some things like the alcohols, methanol and ethanol, which we've detected pretty widely, we'll use a technique called headspace gas chromatography. And this is literally borrowed off of same type of practices that are used in forensics labs for blood alcohol determination. And again, we apply very rigorous validation protocols to ensure that the values that we obtain from those measurements are reliable. We survey a large swath of metals. There are some targeted compounds such as arsenic and selenium and strontium that we've looked at much more closely. We use techniques such as inductively coupled plasma optical emission spectrometry and mass spectrometry to do this. And with these techniques, we can essentially get very sensitive quantitation of 70 plus minerals and metals. Each one of these metals will give a unique signature in the instrumentation that we use to measure the water quality. So just a little detail on the first study that we did. These were samples that were collected initially in 2011 and in early 2012. We had done 100 water well samples across North Texas just because of the notion that nobody had looked at anything that sizable to that point. And although we used a whole swath of techniques, really to give you an idea of the main finding there is about a third of the water wells contained elevated levels of arsenic, greater than 10 parts per billion. Now, water in Texas generally has historically, always does contain some arsenic, but it never approaches, at least historically is shown not to approach this level. And this arsenic is coming from natural formations. But when that arsenic level gets above there, there's plenty of research to show that this is extremely carcinogenic. Especially long-term exposures can cause serious problems leading to things like bladder cancer. We had detected up to 16 times that minimum level in one of the samples, and we didn't find any arsenic over the levels in some of our control sites. What we found, if you look here on the right, is a plot of the arsenic concentration as a function of the distance to nearest gas well. And so what this is telling you is that as you get closer to a nearest gas well, you have a higher propensity for the arsenic concentration to be above that threshold level, which is that dotted line of 10 micrograms per liter, 10 parts per billion. And you can see there on the left that of the large historical data set that we were able to compare to, again, we were not able to collect baseline data because of all of the activity that was in the area, but you can see historically levels of arsenic had not exceeded this. We go on to posit in this paper a number of ways that the arsenic could have been mobilized. Probably the most reasonable case is that this was an indirect release of arsenic from older water wells. Arsenic can co-precipitate with rust, with iron in rust and scale, and with a raise in pH and a more oxidizing environment, you can have a solubilization or a release of the arsenic back into the water. And so we considered this to be, out of all of the avenues that we evaluated, the most reasonable explanation. So kind of an indirect relationship to the increased activity in conventional drilling. We have since then, this paper has just come out earlier this year, literally 3 months ago, where we have expanded from 100 now to 550 water wells across the Barnett Shale. And you can see even if you look at the red dots in the plot, that the light gray areas of the Barnett Shale, those dark gray dots are all oil and gas wells. and then the red dots are all the sampling sites. And we've been honing our analytical skills. We've got a very comprehensive measure, and then we went out and conducted one of the most comprehensive groundwater monitoring studies that is the most comprehensive that has been done to date. You can see how these samples are distributed over different counties in North Texas, and as well as residential and public water wells and agricultural wells. Out of that list I showed you from GCMS, we came across a significant number of abnormalities. Those highlighted compounds are ones that we did have significant numbers of detects for. And you can see the green ones are detections, but there has not been a maximum contamination limit value established, which in some cases is quite surprising, because you can see things like more than half of the samples contained levels of significant levels of chloroform. This is not something that you want to have in your water. You can look at detects where we had of certain BTEX compounds, these toluene, ethylbenzene, and xylenes, where they were detected but at levels below the maximum contamination limit. And then a number of compounds where they had maximum contamination limits established, such as for benzene and dichloromethane. There were exceedances of this limit. So certainly some cause for concern, some significant abnormalities. There's copious amounts of literature regarding the amount of there's copious amounts of literature regarding the hazards associated with some of these chemicals. Here is just summarized a number of the different detections that we've had for a select few of them. So again, just kind of emphasizing, we've developed all of these methods to be able to look at abnormalities in water, and then, from then, we are not toxicologists, but there's plenty of data that we can plenty of data in the literature that shows that having things like these compounds in your water are not good. But yet there is not any stated maximum contamination limit for this particular set of compounds. And so this is something that we think of our research is able to shed light on, is more work that needs to be done from the toxicologists to understand, or at least to set some limits for these. I mentioned a little bit about working with efforts to do remediation. This is kind of a lead into something like that. We did take the opportunity to look at even some bacterial characterization in the water, and we found a couple of these bacteria listed up there at the top left that were present in a few of the water samples. And those water samples also had some significant numbers of those chemicals that I just had listed and shown before. Well, okay, these particular bacteria are not supposed to be in your water, and some can have adverse health effects. But we figured that, character is one thing, but also this is a potential way to consider how an organism like this might be able to help degrade or be a biodegradant, an engineered biodegradant, if you like, for degradation of some of these chemical constituents. If they're living in the presence of it, then they've been able to use it potentially, and if they use it, then they can get rid of it. So shown on the right is just some preliminary data that we've in the laboratory using these organisms to study the degradation of some of these chemical constituents. And so this is an area that gets more into the remediation side of our CLEAR acronym, and that's really an area that we feel is going to be very important in the future. We don't want to be just pointing out problems. We want to provide some real solutions, and I think we can do both of those very well. So I'm going to hand back over here to Zach for him to finish up the talk.
All right, thanks, Kevin. I'm told here that we're having a little bit of technical difficulties. The audio is going in and out, but I appreciate everyone bearing with us. If you have any questions, please feel free to write those into the question section, and we will address everyone's questions at the end of the presentation. So just to stay tuned. So as we discussed, we've done extensive work here throughout the state of Texas, primarily in the Dallas-Fort Worth area. But what we're finding is from those reconnaissance efforts, we need to really dive into unique mechanisms for contamination to understand, how are these contamination events occurring, so perhaps we could prevent them or limit their occurrence in the future. So we've collaborated with the different universities to do a reconnaissance analysis of methane throughout the major shale plays, and our recent work in the Barnett Shale has led us to a time series analysis of compromised water quality in a subregion of the Barnett Shale. This is a region, I've got a picture here on the left. This is a gentleman's water well that has a gas vent, which he can light the gas vent on fire because there are so many dissolved gases in the water, but he can also light the water on fire. And folks around him also have chemicals and high levels of thermogenic or methane in their water. What we can use with the various tools is we can determine whether the dissolved gases, for instance, are naturally occurring and are biogenic, the result of a microbial metabolism, or if they are thermogenic and are a result of some kind of energy layer, whether it's an intermediate oil and gas layer or deep shale layers. Then we can go in with the forensic tools to understand and do isotopic analysis to see if there is a signature match between the carbon atoms in methane of the gas in people's water wells from the gas that is coming from the nearby oil and gas wells. So with these techniques, we can really understand how the contamination is occurring. This has also led to the development of some new technology with a company up in Canada called EOSense, and with their help we've developed a methane sensor which can monitor methane levels in real time, which is incredibly enlightening. Here we're having, sorry, bear with us folks, we're having some issues with the audio. Are we back online? Okay, we're back here. With EOS, are we fading in and out? Okay, we're good now. Thank you, folks. With EOSense, we're developing this methane sensor which can monitor methane levels in real time. And this is really a Sentinel analysis to not only understand the methane concentrations every hour of every day. It can identify problems in real time so that we can potentially do more elaborate studies as quickly as possible. But we can collect more data in real time. So we can have thousands of these sensors out in the state of Florida. We can put these sensors out throughout the region and be monitoring methane in real time. All that data can go to the cloud, it can go straight to your iPhone, and then if we find a region or a sub-region that is having some high levels or spiking of methane levels, then we would want to go in and do something about that right away. The conventional method of doing this is to go out and collect samples in the field, and for dissolved gases you're looking at hundreds of dollars each time, whereas you can implement this sensor and be collecting measurements every 15 or 20 seconds. So it's really going to be a nice development for the environmental scientists using this out in the field. We talked about our work in the Barnett Shale. Now I'm going to talk about some of our work in the other shale formations. Here's an analysis in the Cline Shale of West Texas, where we've actually been able to collect some measurements before, during, and after the inception of drilling. So in Florida, where they're looking to potentially implement unconventional drilling in a region, if they were to go through with that, one would expect them to go forth and do some baseline testing, and that's what we've done here in the Cline Shale. So here's an image on the left showing a subregion of the ranch where there are no wells. 2 years later, there are now 3 wells within a stone's throw of each other, and what we've been able to find is in this particular study is that there have been a large number of changes, but that these changes fluctuate in a rather transient or ephemeral nature. So if I go through this timeline in chronological order, we started in December of 2012 where we collected samples from 40+ wells. There was only one unconventional well in the region that had been drilled 2 months before we actually got out there. So that's something to keep in mind. But what we found is that the pH of the water was relatively neutral. It had a pH of 7.4, which is normal for that region. It had a total organic carbon level of 3.9 parts per million. We did not detect any alcohols. We did not detect any bromide. We did not detect any dichloromethane or any of these other organic solvents that we found. Very important to keep that in mind. We come back months later, there had been 6 new wells in the region, a total of 7, and we found that the pH of the water had spiked from 7.4 to 8.7. Coupled with that, we also found that the total organic carbon increased from 3.9 to 16.2, which was an indication that there's some kind of organic matter in the water. All of a sudden, we detected some of the alcohols, and we detected dichloromethane in almost all of the wells. Dichloromethane has been implicated in air quality being compromised near unconventional wells, but this was one of the first times that we'd ever discovered dichloromethane in the water. And if you'll remember from a couple of slides prior with Kevin, I mentioned that we detected dichloromethane in 121 samples of our 550 in the Barnett Shale that were above the drinking water standard. Additionally, we detected acetaldehyde, cyclohexane, toluene, propagyl alcohol, MP, and O-xylene isomers in multiple wells. As we continue on into the time series in our third phase of testing, we then found 12 unconventional wells in the region. The pH is still elevated at 8, but is now coming down. The total organic carbon has dropped completely, likely the result of bacterial communities using that carbon as a food source. And then we start to find more of these alcohols in the water. We start to detect bromide in the water, and there are still some of these chemicals that are persisting. At this point in time, the dichloromethane had been completely metabolized, and what we find is that dichloromethane can break down into other compounds like formate, which we had detected in subsequent steps of this analysis. We go to the fourth phase. We find now there are 15 unconventional wells in the region. The pH has dropped to completely neutral, what we found before. The total organic carbon is down at a normal level. We still find some of these chemicals in the water. And what this data illustrates to us is that when there are contamination events, and in this case, the only thing that had changed over this time course was the drilling activity in the region. It's a rural community where there's just farming and wind farms. The only thing that had changed was that there were unconventional oil wells in the region. So when there are contamination events associated with this process, there is going to be an immediate influx of chemicals, but those will be metabolized over time. So it's important for us to understand the time life of contamination events. Okay, I'm just getting word here that there are no questions in.
There's a chat window.
Oh,
they can use the.
Okay, I'm told here that to please use the chat window if you have any questions, and again, we'll address those at the end of the presentation.
There's a specific question window.
Okay.
And then there's a separate chat window.
Okay.
For passing general information.
Okay. Sorry, folks. So there is a chat window and a particular question window, and if you have your questions that you would like answered, let's go into the chat window. Okay, questions go in the questions, and the chat go. I apologize. We're scientists here. We're not audiovisual professionals. Nonetheless, I'm going to get right back into the science. In our recent study in the Eagle Ford Shale, this is in South Texas, we've collected 78 samples from private and public water wells. This is the first time that a team has gone down into this region to analyze groundwater quality. And what we found is quite interesting. So we didn't find chemical contamination to the same extent as we found in the Barnett Shale, although we did find some of the same compounds, chloroform, propagyl alcohol, ethylbenzene, and we found some new compounds, 2-butanone, tetrahydrofuran, cyclohexanone, and we also found high levels of methane. These new compounds are likely attributed to the fact that the Eagle Ford Shale is an oil play compared to the Barnett Shale, which is primarily a gas play. So there's going to be a difference in the chemistry there. An interesting thing that we also found is when we look at chloride to bromide ratios. And chloride to bromide ratios, again, these are naturally occurring ions, chloride more prevalent than bromide, is when you look at the ratio between these two, they can give you an indication of if there's been any kind of mixing with industrial brines or salt solutions or even sewage. And I've got an image here on the left looking at chloride-bromide ratios throughout the Barnett Shale, and it's a very nice spread where you look at unimpaired groundwater. You've got mixing with oil field brine, some instances of dissolved evaporates being contaminating groundwater, and then also instances where the chloride-bromide ratio is indicative of brominated gasoline. Well, in this Eagle 4 data set, what we found is there are really only two distinct populations. There was one that could be considered as normal, and one that had a disproportionately high level of bromide compared to the chloride. This can be indicative of the use of brominated gasoline, and gasolines and diesel fuels can be used during the stimulation process. Interestingly enough, of these 12 high bromide samples, 11 of the 12 were located within 1 kilometer of a nearby unconventional oil well. So we're working through this data right now to characterize exactly what has happened here. Is there any other new details that can provide insight into how this occurred? But it is very interesting, something that we've not seen in prior formations. The moral of the story is, in all these areas that we go study, we always find something weird and wonderful, so to speak. We've never gone into a region and not found something. And so with that information, you can make intelligent decisions about the practices. And again, we talk about remediation and fixing the problems as soon as possible. So we've talked a lot about water. I'm going to get into our work in soil analysis, primarily looking at BTEX compounds. And again, this is benzene, toluene, ethylbenzene, and xylene isomers. These are found in natural gas, crude oil, gasoline, diesel fuel. They're also used as independent solvents in the stimulation process. And a lot of these are carcinogenic. For example, benzene can lead to bloodborne cancers, acute myeloid leukemia, acute lymphoblastic leukemia, and the drinking water standard is 5. While there is no standard for benzene in soil, the exposure to benzene is something that you would want to limit at all costs. So if we look at some of these saltwater disposal wells, or these underground injection wells, if you will, we've collected some samples on these sites. And as you would expect, it's not going to be a perfect process. There's going to be some spilling of some of these waste materials, and you would expect to find these compounds in the soil. And that's exactly what we found. The work by Dr. Carlton shows that these are found in high concentrations in the soil, and we're talking about surface soil, so the first 6 inches of soil, but we're trying to understand whether any of that may have the potential of penetrating down into shallow aquifers. This brings us to our Eagle Ford case study. We've been working with a number of ranchers out in the Eagle Ford Shale to characterize air, soil, and water quality. Here's an area where we're working with a number of different families. There are 8 pad sites, which are facilitating 28 different horizontal oil wells. And these are coupled with gas flares, which I'm going to show you some imagery of in a minute. So there's basically a highly industrious process going on here. So the thought is, are these different processes, the gas flaring, the condensate tanks, the in and out of trucks, is this having an effect on air, soil, and water quality? Using some really novel technology referred to as mobile mass spectrometry, we have a mass spectrometer in a smart car, an electric car, where we're actually able to collect measurements for volatile organic carbons, these BTEX compounds, polyaromatic hydrocarbons, things like naphthalene, in real time while driving a car 70 miles an hour. So basically, using this technology, we've been able to go on some of these pad sites and identify if there are any issues. Now, what we have here is a heat map representation of concentrations anywhere between 0 and 5 parts per million of BTEX compounds in the air. And so as you can see, the green portion, there is not much BTEX there, but as you get into the red dots, that's where these BTEX compounds are concentrated. And what we find is that all of these pad sites, these 3 sites you're showing, all of them have the same processes. They all have the condensate tanks where oil and water is separated. They all have gas flares where they're burning off residual natural gas after acquiring oil. But some of them are better than others. So we see the one on the left. There are multiple instances with high BTEX around this pad. Same with the one on the bottom right. We see that these red dots correlate mostly with proximity to the flare, but there luckily are also some pad sites that are not so bad. You know, we see the one here at the top center where there is compared to the other two pad sites, very limited BTEX being emitted from this pad. So this is certainly encouraging from an industrial standpoint that the process could be efficient. However, we are also finding a large occurrence where there are inefficiencies. If we look at the implications for soil quality, and here I have things color-coded, a white dot means that there are 0 BTEX detections in the soil, yellow is 1, orange is 2, red is 3 BTEX compounds, and blue symbolizes that all 4 BTEX species have been detected to some extent. And what we find is that around some of these pad sites, where, as we would imagine, the bad apples, the bad operators that are emitting a lot of VOCs from these pad sites, we also see that there are a high concentration of these compounds also in the soil. And what we didn't anticipate is that as you get away from these pad sites, these BTEX compounds also persist in our control areas. So as you get further away from these pad sites here, particularly in the top left, you see a lot of blue dots on one particular portion of the ranch. Clearly, with these flares and these condensate tanks running 24/7, they are emitting into the atmosphere all day long, and what we're finding is that is likely percolating slowly but surely and concentrating into the surrounding soil. In this case, the wind is coming out of the south, so what we're finding is a majority of the BTEX compounds are found on the north face of the ranch. So we follow up with this analysis every 3 months to see if there have been any changes. We want to understand how quickly these things are broken down in the environment. And we are also testing further out on the ranch to get a broader understanding of how wide the contamination in the soil may be. So the conclusion here is that these BTEX compounds are much more prevalent in and around these unconventional sites than we previously anticipated. And we believe that because we can get up to close with this real-time mass spectrometry, we can actually source the chemicals. So those are likely attributed to the flaring stations and the condensate tanks that are on these pad sites. Again, this is resulting in BTEX volatilization. I have an image here of a gas flare. So this is one of the pad sites where a large number of the soil samples around it had been contaminated with BTEX compounds. And as we can see, some of these flares burn very clearly where there's not much black smoke. Others do burn what's called a dirty flare, where you have a lot of black smoke, and we believe those ones that are burning with that black smoke are the ones contributing to the BTEX in the surrounding areas. So I'm going to talk a little bit more, coming to the last couple slides here. So if we look at prevention of contamination events if drilling occurs, obviously if Florida and other areas, other states, other provinces in Canada or other countries were to go ahead and engage in unconventional drilling, it would behoove them to collect the baseline measurements so they have a reference to go back on if there is a contamination event. We also believe that continuous monitoring and testing during large bouts of activity after wells are drilled is incredibly important to continually monitor environmental quality. Ideally, it would be in everyone's best interest for individual operators to have color-coded tracer compounds that we could differentiate based on UV absorption or using a flow cytometer or a spectrophotometer. However, that would require a great deal of collaboration with industry, something we very much have extended the opportunity of doing, however, have not received much success in doing so. It would also be in everyone's best interest to have full chemical disclosure. So while there is trade secrets, there's proprietary information about what is going down the well to stimulate these wells. If there are cases of contamination and you're talking about chemicals that can be deleterious to one's health, it would be important for those who are either afflicted with groundwater contamination to know exactly what to look for so that they can run those tests. As Dr. Shug has alluded to, a lot of the times we've been operating in the dark. We've had very little information from fracfocus.org or from a congressional hearing on hydraulic fracturing where they describe very limited information about what is being used. However, there can be a lot of idiosyncrasies of an individual well that require different chemicals, and so we don't really know what those are. So when we screen water samples, they will pop up as unknowns, which we can ultimately go in and characterize, but if we knew what we were looking for, it would make our job a lot easier. As I alluded to with that air and soil quality stuff, flaring is contributing to VOC emissions, BTEX emissions, and so in Florida, where it's going to be primarily an oil play, again, if this goes through, that you would want, there is going to be some residual gas, you would want to capture that gas as opposed to just burning it off into the atmosphere. There has been a number of papers showing that flaring has about a 98% efficiency, but still you're talking about cubic feet of methane flowing into the air that have not been destructed by the flaring process, and methane is a potent greenhouse gas. Accident preparedness funds and remediation being very, very costly. I showed it early on in the presentation a case of a well blowout in Kennedy in the Eagle Ford shale. Accidents happen. By an industrial standard, accidents happen all the time. You just have to be prepared for them. So in the case of a well blowout, certainly if it's not handled appropriately, there can be an immediate injury. However, over time, there can also be injury if proper remediation isn't initiated. So we're talking about soil quality remediation, water quality remediation, and air quality remediation. We're working with a number of new technologies, new companies to develop these best practices, these strategies that can help sequester these exogenous compounds, these chemicals in the air, soil, and water, and then extract them out so that the air, soil, and water can be remediated back to a natural state. The interesting thing and somewhat of the concerning thing about Florida is that because of the very porous geology, the limestone formation, underground has a very cavernous nature. We believe that it requires more testing and much more frequent testing because there's a greater potential for contamination events in that region. This is certainly something to keep in mind. Here in Texas, we have areas where there are naturally occurring fault zones that are less advantageous to be stimulated in, and so people generally avoid those regions. However, if you have a region where there are caverns and there are fault lines and there is limestone, there's a lot going on there, so there's a lot of consideration. But if things do go through, we believe that because of that, those factors, you will want to be doing a much more thorough analysis and much more frequent analysis. In terms of remediation, again, when you do the analysis out there, swift action needs to be taken forth to remediate those contamination zones. Obviously, we touched on this before, testing before, during, and after remediation to assess what needs to be remediated, and then also to assess the quality of the remediation effort. Subsequent testing in preceding years after the remediation is a good idea, just to make sure that environment has been returned to its natural state. And that one thing right there is that it is possible during contamination events that remediation can be result in the environment being returned to its natural state. It requires a highly collaborative and articulated effort, but it can be done. We are showing this in the lab, and we are doing this out in the Eagle Ford region. So there is hope if there are contamination events. So the future directions for our team and where we see this research going is, obviously, we would love to expand into other shale formations outside of the state of Texas. We began work in the Haynesville Shale that borders Texas and Louisiana, but obviously Florida is a very interesting geology that we would love to contribute scientifically to in terms of testing, monitoring, and best practice management. We're also very much enthused by the fact that we can develop new technology and these new remediation strategies for instances of drilling-related contamination. What we've learned in the Eagle Ford Shale is something that could be translated into efforts in Florida, as they could be translated into efforts in Alberta, Canada. If you understand what you're dealing with, then you can apply the appropriate strategy and then it's just a matter of going through it systematically. We're working with a number of different companies for remediation and recycling. One based out of El Paso, Texas is American Water Recycling, where they utilize thin layer graphene filters to pull out contaminants from water. Also working with a group out of Calgary, Canada, called Pure Life Environmental Solutions, where they're looking at recycling and reusing produced water and flowback waste so that they can use it in subsequent wells to re-stimulate. So this would ultimately result in a lesser reliance on fresh water, which I think we can all agree is a good thing. And then we're also working with a number of companies, mainly EOSense. Here we're talking about in situ, in place, in field detection of environmental abnormalities. In this case, we're talking about a methane sensor. So a lot of these Sentinel efforts to provide us with more information so that we can provide a more targeted analysis out in the field. So with that, I just want to thank everyone for their interest, their patience, and I'm going to open it up for questions and answer any questions and concerns that you may have. All right. So we're going to go straight to the questions section. Kim, okay. Okay. I'm going to go ahead and read them, and then Kevin, here, I'll bring this over here. And Kevin, you can go ahead and answer them.
We can both answer them.
Okay. Let's take a question here from Rosalind. The companies that want to do fracking and oil and gas, many other environmental processes, give assurances that they are safe and they will monitor for contamination or problems. However, once they detect the problem, contamination, etc., it is too late. The Deepwater Horizon is a prime example. How can this be addressed better upfront to prevent activities that might result in such problems?
So this is an interesting question. It makes me think of, I had an opportunity actually to go down and visit Colombia. The government of Colombia convened a number of experts around research that had been done on unconventional drilling, as well as stakeholders in the oil and gas industry, and were very much involving environmentalists. And they had worked together to develop a very stringent series of regulations by which it seemed agreeable to everybody that the unconventional drilling could be done in an environmentally responsible fashion. To me, I think that seems like the best way to go, that everybody is open, that there are channels for people to be able to see the data that's being collected, that multiple eyes can be able to evaluate that data. To the issue of, once there is a problem, is it too late? We've seen instances that we presented today about spurious contamination events that may be indirectly related. We've seen some pictures that have shown of massive blowouts, and yes, I think that everybody can understand that in an industrial process of this magnitude, there can be problems, and maybe in some of those cases some major damage can happen. But I think that adhering to best practices that are guided by responsible regulations, as well as a careful monitoring that is done by multiple institutions, not only just the operators but also additional outside groups, is really the best way to go to help mitigate especially smaller problems and to make sure that things are being done correctly.
All right, I'll take this next question. Isotopic analyses can be tedious and expensive. Yes, they can. Can the presence of butane and propane be used to differentiate between biogenic and thermogenic? The answer is yes. So when we're talking about biogenic gas, referring to biogenic methane, it's primarily methane. When you have thermogenic gas, it's going to contain propane and ethane in higher concentrations. So that analysis is easier to do and cheaper to do. You get into the isotopic analysis, it takes longer, it's more expensive. And so if you're to do baseline testing, you would obviously want to start with just the basic hydrocarbons, which would be methane, propane, and ethane. Another question here, we'll have this one for Kevin. Once contaminated, can a water well be remediated?
So I think the nature of the contamination and that determination is really the key piece. I mean, we've talked about instances where methane has contaminated water wells, and the response is to include venting systems to remove the methane. That's a pretty expensive measure, and some people could afford that, and some might not be able to. You know, in terms of remediating chemicals that are associated with, you know, things like BTEX chemicals, I mean, filtration technologies have, there are graphitic systems out there that can be used for filtration. I think probably, really, it depends on an assessment of what is contaminating that system. Zach, do you have anything to add to that?
Yeah, I think you touched on it. I mean, it depends on what the problem is. Certainly, if we're dealing with metals and ions, we can implement reverse osmosis filtration technology. If we are dealing with chemicals, we can use these charged charcoal filters. However, we are working with this bioremediation effort where you can utilize innocuous bacteria to go in and metabolize these things. The answer is yes, you can use filtration technologies to restore the water to its original quality, but to do it on a larger scale, the remediation, in situ, we're still working on those technologies, not quite readily available at this point in time. Okay, this one. What distance from the well site do you recommend using for baseline testing? You would want to be collecting samples close, intermediate, and far away from the nearby oil or gas well in question. A lot of baseline testing is done within 2 kilometers or 2,000 meters of a nearby oil and gas well. However, we found that up to 5,000 meters, 5 kilometers, can result in contamination. So you're going to want to get a wide range at varying distances to really understand the groundwater quality. Okay, I'll read this next one. On wells that failed and have not been active for several years, could they be leaking chemicals, and should the water be tested? The answer to that is yes. So we talked about well casing failure, and the well casing is basically the protective layer in between when they penetrate through the aquifer, between the oil and gas process and the aquifer. So if that casing fails, then you could have contamination where as the chemicals go down and the gas comes up, it could be spraying laterally within the plane of the aquifer. Now what we find is that protective casing is supposed to be protecting all potable layers of water. In Texas, for example, if you have water at 300 feet, 500 feet, and 700 feet, then you should be putting protective casing well below that 700 feet to ensure that, again, you've got no casing issues. And the casing is going to have thorough analysis over time to make sure that the pressure hasn't been lost, which would be indicative of casing failures. However, we are finding in some cases where they may be casing only down to 300 feet, yet there's water levels at 500 and 700 feet. In those cases, those are operators just cutting corners, and there can be contamination if they don't case through all of the layers of water. Then when you look at the casing failure rate and the integrity of that casing, you know, there's an initial analysis, and I can't really speak to how frequently that is tested, but it stands to reason that there's a 12% failure rate within the first year, that could increase in subsequent years. So yes, I mean, in those areas where there are older wells that have been plugged or they're not doing anything, it would behoove us to go out and do some testing just to figure out if there's any link between that activity and the groundwater quality. Okay, here's a question. does the on-site remote monitor have enough sensitivity to tell you which sites are the best candidates for more extensive studies? I'll answer that one. So basically, we have the sensitivity to go down to 1 part per million methane. So the threshold, what's considered safe by the Department of Interior, is 28 parts per million, or 28 milligrams per liter. So if we can go down to 1, you might expect there to be low levels of maybe biogenic methane, and you would just continue to monitor that over time. But all of a sudden, if you saw a spike to 10, 15, and 30, then you would want to go in immediately and do some testing, not only in that well, but in surrounding wells, to, one, understand where is this methane coming from. You do the analysis of methane, propane, and ethane, just to understand, is this biogenic gas, is this thermogenic gas, and then you'd want to do that. If it is thermogenic gas, then you'd also want to look at some of the chemical compounds that could be associated with the drilling process. Would it be useful to publicize to people leasing drilling sites that they require in their lease that companies use tracers?
So, I mean, I think that's a very interesting idea. In fact, we talked about wanting to work together with industry, and we put out a number of proposals with various companies, and unfortunately we've been unsuccessful. But one of the concepts that we really feel that should be pursued, and we know that there are other people who are thinking about this as well, is that the incorporation of tracers in different parts, different phases of the unconventional process could be very useful in trying to understand if there was a problem, where it was coming from. So, whether you can require the industry to use tracers, I think it's certainly worth trying. I think that there are groups like ourselves who would be very willing to step in and try to work with those companies to ensure that those tracers are designed well and can be tracked appropriately in the intent that they're meant to be used.
Next question. Has there been an official public health reaction to the high arsenic levels found in the DFW water? So this is an excellent question. Basically, this is the genesis of why we're in this field of research, is to provide people who have questions and concerns about this process to allow them to make a more intelligent and informed decision about unconventional drilling. Again, we're a neutral group of scientists. We are not environmentalists. We are not industry advocates. We have to stay neutral and objective on our water quality data. And so we provide this information and allow the masses to utilize it. And we have been contacted by the city of Arlington, for example, city of Fort Worth. There have been a number of entities, TCEQ in Texas here. We have Texas Commission for Environmental Quality. They have inquired about some of our work in the Eagle Ford Shale, for example. Environmental Defense Fund has done so as well. So we certainly make ourselves readily available if anyone has questions about the data. However, we do not push it upon people to glamorize the data. We just make it available so people can make more informed decisions. All right. A question here for Dr. Shug. Would it be useful to conduct soil monitoring studies in Florida?
Soil monitoring is something that we've started doing recently in Texas, and I think absolutely. The soil analysis is a different animal than water analysis and air analysis, but all of these different these are all things that are connected together. And if you're going to have instances of water quality contamination, and this is potentially associated with a spill or a surface spill, then you want to understand the extent of that surface spill, and by doing soil monitoring you can do that. I think that, to be honest, a more comprehensive approach is not only water quality and soil quality, but also air quality monitoring. I think the more information that we have going through this, the better. Certainly, I would say water quality baseline measurements is something that people understand and are propagating. You see this more in different regulations of different states. The water quality monitoring is more, people understand what to look for. I think that the soil quality monitoring is something that needs to be taken to that level. and has just as much a potential to provide useful information on environmental impact.
All right, here is another question for you, Dr. Shug. Regarding the PLOS manuscript currently in review, and again, folks, that is the manuscript describing time series analysis before, during, and after unconventional drilling in the Klein Shale. Will you submit this directly to the EPA?
So, first and foremost, where we feel that our place here is to publish results into the peer-reviewed literature, and that's what's referring to this PLOS manuscript. PLOS One is a well-regarded peer-reviewed journal in the sciences, and that timescale study from the Klein Shale is one I think that's going to be of significant interest because it is the first time anybody's been able to look at an area before, during, and after drilling. And Zach explained, some of the very spurious finding, the ephemeral changes that can occur during these those processes. Will we submit it directly to the EPA? I'm pretty sure that they're gonna find it and study it themselves, and we'd be happy to talk to them more about the details if that were necessary.
Yeah, in fact, the EPA recently did a 5-year study of unconventional drilling and hydraulic fracturing. And our papers were a number of the ones that were listed as sources of information for that report. Okay. Great question here. This research, who is funding this research? So we're actually scientists of the people. We have been very lucky to work with some great landowners, ranch owners. These are folks who have concerns about environmental quality on their property and also throughout the region, who have donated to CLEAR to have made this research possible. Unfortunately, this research is incredibly expensive. It requires a lot of people, and it's a tremendous undertaking. But thankfully, we've had excellent support over the last 5 years to be able to do this and to really dedicate ourselves to new developments in terms of remediation and detection side of things.
I'll just add to that this is something that when we started, we looked around as a traditional, academic endeavor. You'd go and look to foundations and the federal government for funding of this research, and it really is not present like you can go and get a research grant to study aspects of cancer or some other disease. So we really had to. This is really one of the points for defining this consortium of CLEAR. Through University of Texas at Arlington and the other partners that we have, Inform Environmental, and so we really do rely on having input and donations and support from the people to be able to do this work.
And as per that question, would like to hear cost data for real-time methane monitoring, both one-time acquisition, deployment, and reoccurring for operation. So, great question. So the methane sensor that we're working with, again, it's something you plug on your well. You can continually be running a low feed of water into the system. It can be collecting measurements every 10 seconds, 15 seconds, which can go to the cloud and straight to your iPhone. These systems, we're working on to get it down to $1,000. And that would allow us to get these systems, make them more affordable for municipalities, concerned citizens, to get them out into the region to keep getting as much data as we possibly can. Compared to historical measurements, you go out there, you collect an on-site measurement for methane, it can cost a couple $100, and if you get into the isotopes, you're looking at maybe $500. So by doing the continuum monitoring, it allows you to monitor general water quality, and then if you find any abnormalities, then you can spend the money to do a much more elaborate analysis. Okay, we've still got lots of questions here, folks, and please feel free to chime in. Can we set up a methane detector array in heavily impacted areas with topography, like my home state of West Virginia? Yes, absolutely. The versatility of the water quality methane detectors allows us to put them anywhere, under any conditions. It's manufactured and developed in Canada, where it is very cold. There are blistery conditions almost all the time. I can say that with confidence because I am Canadian. And what I can say is they're incredibly robust. Now, with the air quality measurements where we use the mobile mass spec, we can drive our car at any time through any conditions, as long as the car doesn't break down and have tires get exploded, like what can happen in the rocky roads of the Eagle Ford region. But the technology is incredibly robust and gives us a lot of capabilities to sample under various conditions. Okay. Here is a question. Bromide is used as a non-reactive tracer in a lot of subsurface hydrogeological studies. For studies involving bioremediation, we typically would start sampling for other components, organics, metals, following the breakthrough curve from bromide. Have you sampled any well where concentration of bromide started low and then increased with time? I'll answer that. So in our time series analysis, yes, in the Klein Shale, we, along with those volatile organic carbons, we didn't find the bromide detections in high concentrations until the third and fourth round of testing, well after there had been more than 10 wells in the region. So yes, we had seen fluctuations, and it's adds to the multiple lines of evidence that the drilling activity in the region had affected the quality of the water. Okay, have you analyzed samples for the presence of crystalline silica downwind during flaring? No, but how would we do that?
So I think I've heard talk about the some emissions from collection site can potentially contain these pieces of proppants that are released back up. This is not something that we've looked at closely to this point. We have talked to a few people about it. It is possible to set up air filters where, with a very well-defined flow across a fiber filter, you can collect particulates and then bring those into the laboratory to analyze them, and also be able to do this over a particular amount of time period so that you can understand the length of a release. It's not something that we've looked at yet, but it's something that we've heard about.
All right. Okay. Will webinar be available after broadcast? Yes, we are going to make this available hopefully on our website and also on YouTube. Okay, we're going to go through these remaining calls here pretty quickly, but again, these are excellent questions. We really do appreciate your feedback. Why are flare stacks so tall? To protect the workers. So in that one image I showed, it was about 20 feet tall. I imagine that certainly is a concern. Some of these are 5 or 6 feet off the ground. There's varying configurations, if you will. How expensive is it to plug a horizontal well? Well, these horizontal wells, to begin with, are upwards of $8 million investments, and I can't speak to how expensive they are to fix and to sort of plug and stop, but I imagine you're dealing with hundreds of thousands, if not millions of dollars. Okay, are you able to determine what is most vulnerable to contamination? Water, soil, and air. What we're finding is that air and soil seem to be the most vulnerable to contamination. We are finding that these compounds from the surface can percolate into the shallow groundwater. If you have a case of drilling waste that has been spilt on the surface, it can percolate down into shallow groundwater. But then again, when you do have the subsurface activity of hydraulic fracturing, it is also contributing to cases of contamination. So I would believe, because of this process being highly industrious, that all three of those environments can be affected, have the potential of being affected. Question about costs per sample. So if we were to do a full analysis of dissolved gases, metals, minerals, anions, and chemicals, we are looking at anywhere at approximately $1,000 per sample. It is incredibly expensive, but we're detecting these compounds down to the parts per billion range, 1 to 2 parts per billion. And so to have that sensitivity and to screen for that range of chemicals that are relevant to this process requires some pretty advanced instrumentation. Okay, what sort of effective remediation of VOCs in neighborhood air is proposed? Once released into the air, how can VOCs be recaptured? So this is one thing that we are currently working on, where we have a lot of success in soil with the acquisition of VOCs and the sequestration of VOCs with charged charcoal. It's the same technology that people use in filters. We believe that we can use similar technology, maybe perhaps with a vacuum system, to sequester in these rogue VOCs from the air into somewhat of a charcoal sphere, and then that sphere can be interchanged over time. This is something that we're currently working on, and it's going to require a little bit more development. Okay, I'm still going through lots of questions here. Do you have any cooperating academic partners in the state of Florida? Is the University of Florida, for instance, involved in as a cooperating institution? As of right now, we do not have any entities that are working with us in Florida. Again, we have aspirations of helping the state of Florida in addressing the concerns about unconventional drilling, and this opportunity for this presentation was just for us to inform folks of some of the potential implications in that region.
I'll just mention that, as I said before, CLEAR is a consortium, and we are always actively adding, looking for people that we can work with, particularly, you know, for example, University of Florida, if there were individuals there interested in working and could provide a unique expertise beyond what we're doing currently. We're certainly open to working with other groups. This is a very common effort for us to be collaborative and open to working together so that we can put out the most useful information possible.
Yes. Okay, question, and we've got about 10 more questions here. Who pays for the cleanup once legacy wells fail? That's certainly an excellent question. In some cases, the operator is obligated to clean that up. In some cases, there are also environmental funds for that. It really varies state to state. However, if you have this high level of information and you can attribute a contamination to a particular well, like we have the capability of doing, then if there is that contamination event, then we're able to provide insight enough so that they can obviously be obligated to pay for the cleanup. If we extract and combusted all available or proposed shale gas, what would be the impact on the global climate? Obviously, there's a tremendous amount of shale gas in the United States and across the world. Methane, propane, and ethane are very potent greenhouse gases on their own, but once combusted, they obviously contribute to other greenhouse gases. It's really hard to quantify that. That's a little bit outside of our field of expertise, but we do understand that some of these gas flares, where they are flaring this methane, and even though it's being combusted, it is contributing to a change, a climate change effect. Okay, a question here real quick. I'm curious as to how many attended this call. Literally thousands of people from many different countries are part of this call. No, honestly, we've had a very strong following throughout across the states. We had some folks from Canada come in, and we do appreciate your questions and concerns, as this is a highly relevant issue. Certainly one of the most relevant issues in terms of climate science in the 21st century. Okay. In Florida, in areas where the Floridian aquifer is not confined by a semi-permeable aquiclude, are fracturing methods prudent or feasible, or more importantly, remediatable? Well, that's a great question. As I alluded to, the geology in Florida is highly complex. I mean, you have a lot of limestone, which is porous. You have a lot of caverns. You likely have natural fault lines. And so that unique and complex geology leads us to believe that there is a greater potential for abnormalities to occur subsurface than you would see here in Texas. And so that's certainly something to keep in mind. I would imagine that with it being more complex, it would make it more complex for remediation. Basically, my sense is that there's a heightened sense of concern when we're talking about Florida because of the idiosyncrasies of the geology. Okay. I presume that part of the reason for this webinar is to drum up grassroots support for Florida, and that fracking is not yet widespread in Florida. Yes, absolutely. That's a great point. As we are scientists of the people, and it's been a grassroots effort to expand and help as many people as we can in the state of Texas, we would love to use what we've learned in the state of Texas in these other formations and to help those folks as well. And as Kevin alluded to, we're not just here to find problems and to deliver bad news. We're also here with news of remediation strategies and best practices so that if there is a contamination event, that we can provide a solution as quickly as possible. Okay, are isotopic data a potential method of tracing if given the isotopic signature of chemicals used in unconventional drilling in Florida? Yes, absolutely. So the isotopic analysis is basically looking at trying to source natural gas. So you're able to look at isotopes in methane to differentiate between methane and thermogenic gas coming from an intermediate layer compared to thermogenic gas coming from a shale layer. So yes, we are certainly able to do that. And the nice thing about if we are to have an open disclosure of all the chemicals that are used in the process, then we know exactly what to look for. And so if you find 5 or 6 different chemicals and they all have different roles in the stimulation process, it's pretty telling evidence that there's only one source that could have contributed to that, and that's the highly complex unconventional drilling well nearby. What kinds of isotopic data are available from previous studies? So again, most of the isotopic data has been performed up in the Marcellus Shale. We have a paper where we're going to be describing our isotopic analysis here in Parker County, Texas. These are primarily associated with the isotopic analysis of dissolved gases. Okay, thank you very much. Great webinar. All right, thank you very much, sir. We appreciate all your kind words. Are you aware if any geologists preparing for future research on earthquake activity in Florida limestone? Again, that's a little bit outside of our expertise. There has been heightened awareness of increased seismicity, certainly in Texas, Kansas, and Oklahoma, but to my understanding, that is not of a concern, while perhaps it should be, in Florida. So unfortunately, we do not know of anyone who is interested in doing that work, although I think we could probably find someone relatively quickly. Have you found in areas where there have been earthquakes that there is more water contamination in the surrounding area? It seems like the earthquakes would be fracturing the ground and therefore causing more issues. So these earthquakes have normally been associated with the underground injection well. So when they're pumping down all this waste solution, this brine, it is hitting these fault lines, and when these fault lines are lubricated, then they slip, and then as a result, you have the earthquake. And so also in some cases, like in northern British Columbia and Canada, they also found that the stimulation, actually hydraulic fracturing, had contributed to the earthquake. So it's a little bit of both, in my opinion. We haven't done enough of the research in Oklahoma and Kansas, where those are kind of the epicenters for these earthquakes, to really make that assessment. But where we have found earthquakes in Azle, Texas, in Parker County, we have found a great number of abnormalities found in the water as well. So to understand whether that contamination is coming from an earthquake or from a drilling process, that's something that we go in with a much more forensic analysis to do a detailed screen of the water quality to answer that question. But that's a great question. 50% of casings fail in 15 years. How can anyone consider that this be done safely? Again, with a 12% failure rate within the first year, certainly with an increased failure rate in subsequent years, that's a great question. I mean, how do we ensure that this failure rate is maintained or somehow does not deteriorate over time? That's something that would require a lot of collaboration with operators, certainly something that we'd be willing to provide them with insight on. However, as I mentioned, we've written proposals to work and share data with those entities, and they haven't been inclined to do so. So all we can do is really offer our ability to provide insight, and if they're not interested, there's really not much we can do there. Okay. All right. We have another question about cost. So the question is, for cost, can you please describe the effect of multiple samples? So when we're in Florida, if we were to engage in a project there, we would be engaging not only in certain counties, but it would be kind of spread out throughout the regions where they're stimulating. So the more samples that we collect, certainly we can drop a cost. There'd be an efficiency of cost, but obviously the more samples we collect, we can get a much greater understanding of the water quality. So well, I already alluded to, we want to be sampling for dissolved gases and chemicals and metals and minerals and ions. We would also want to be collecting multiple samples in these regions just to make sure that, from multiple wells to get a greater understanding of maybe if a contamination event is isolated based on the cavernous geology or if it's much more widespread. Okay, at this time, I think we've answered all of the questions. And if at this point, if I'll hand it over to Kim here for some final words.
All right, can you guys hear me?
Yes, we can.
All right, way to go. Thank you everyone for participating. And we just wanted to say that Rethink Energy Florida is, as the Florida sponsor for this event, is very much in support of making sure that we have an informed discussion, and where one of our values is to provide evidence-based information. So that's why we sponsored this. We really appreciate you all taking the time to have this conversation with us, and look forward to additional conversations in the future.
Well, thank you very much, Kim. Again, to everyone out there, we really appreciate this opportunity to discuss the science of unconventional drilling and certainly the environmental implications of this process. That's why we got in this field of research, to provide information so people can make more informed decisions. And all of our material, all of our peer-reviewed publications are available on our website. We provide them on our YouTube channel, our social media. So if anyone has any questions after the presentation, we'd be happy to address them afterwards.
All right, thank you.
All right, thank you very much, everyone. Have a wonderful day.